Welcome to Science Store online classes.
Don't forget to like our video and subscribe our YouTube channel for all the updates.
Welcome to all of you to the physics classes. Dear students, we were talking about magnetism and matter and about some of the topics of NEET classes, and we have discussed the formulations and different cases of maybe the magnetic moment, that especially we have discussed. And after that, while comparing with the electrostatic, what is the force, magnetic force, what is the field, what is the potential, that also we have studied. Here it is magnetic potential, magnetic field and magnetic force, like that. Okay, and magnetic charges is nothing but plus m, negative m you have taken, but it is m itself. Okay, that is nothing but the pole strength we are going to talk about, and in capital letter we are going to denote it as a magnetic moment. Okay, that is 2 into L into m. Those things you have studied, and after that we were discussing about the potential energy and mb, which is equal to cos theta or cos theta 1 minus cos theta 2. Generally, while you are going to apply the formula, you have to apply mb cos theta 1 minus theta 2, because the initial angle minus the final angle. Okay, and negativities. So general formula you have to remember. Now we will talk about the generally about magnetic field and magnetic strength, all those things. Now what do you mean by magnetic field? As we discussed in the case of charge, okay, if some charge is there, another charge you are going to bring, it is going to experience a force. Where it is going to experience a force? Whether say one charge is there, I am going to bring this charge nearer, whether you are going to experience a force? No, here somewhere at the distance, right? Where? Only when it comes, that another charge comes in the field of this, no, that diagrammatically we will write down the field or the range, isn't it? So for a magnet also, in some range will be there, it is having its own field. Okay, so when another magnet will come and it will experiences a force. To visualize that, we are going to write down the magnetic field lines. Okay, so what are the magnetic field lines? So conceptual questions will come in this. Okay, so same, but here it is becomes a closed loop, isn't it? They becomes the closed loop. Okay, magnetic field lines start from, see here they are not going to intersect like this. Okay, there is no intersection. Okay, so they start from north and end at south. Okay, so it is a closed loop. They are going to form the closed loop. So they are not going to intersect. They form the closed loop. They start from north pole and end to the south pole, right? And the direction, I know direction is north to south, but at this point what is the direction? So north to south, I have to write down the tangent. So this is the direction. Now at any point I have to write down the tangent, means I am going to get the direction of the magnetic field lines. So that magnetic field we are going to visualize by writing the diagrams, that is nothing but magnetic field lines. The magnetic field we are going to write down as a diagram, so to visualize that. Now when the questions are come, like for the competitive exam, in what way they are going to ask? So as of now in this, only the numerical sums we won't get here, but only the conceptual questions we may get in certain magnetic field line concept. Okay, so they give the direction, all those things, they never intersect. Okay, that we have studied, and the magnetic moment will be from north to south to north. Inside that it will be like this. Okay, so these are all properties just now I said that we should know. Okay, so that we should know. Okay, this is about the magnetic field lines, and if same poles are kept together and the different poles are kept together, what will be the magnetic field line? So north and north I am going to keep in this way. They are going to repel, isn't it? The like poles are going to repel as same as that of the charge we have written here, 0 is going to come, so neutral point we can say, okay, in this way. But for the north and pole, south pole together means it may be in this way, or else I can write down separate north and separate south pole is means in this way you can write down. Okay, that is the thing. And this is what for the like and unlike poles. But there is one concept is there, that is called magnetic shielding. Magnetic shielding. So any of the materials, see, next we are going to study about, already we have studied in the board exam, that is paramagnetic substance, ferromagnetic substance and diamagnetic substances, right. Similarly, if based on that we have called magnetic shielding. Okay, now I have a ring which is made up of soft iron. Now what happens is I am going to keep a north pole here, I am going to keep a south pole here, means it is nothing but a ring which is made up of from soft iron is kept in the external magnetic field. Now what happens, the magnetic field lines pass like this, magnetic field lines pass like this. Okay, this is found in this way. Okay, so the magnetic field line will pass in this way. Okay, so they will form a shielding, but what happens, they are not going to pass inside the ring, okay, of the soft iron, and this phenomenon is called magnetic shielding. Okay, the same thing happens for the superconductor. Superconductors are the diamagnetic substances actually. Okay, those are diamagnetic substances. If you bring that superconductor to the certain temperature, there is called a critical temperature. Okay, that is a very less temperature. Okay, in -degree Celsius it comes. Okay, okay, now those are you are going to keep in external magnetic field, and for that temperature magnetic field lines does not going to pass through it, they will go away from it. Okay, they not even just touch like this. For what I am talking about, I am talking about the superconductor for diamagnetic substances, but it is not like that. Both are similar, but if the soft iron is kept means, if a ring is kept means a shield like thing takes place, they are not going to pass through it. Okay, so such effect is called Meissner effect. Such effect is called Meissner effect, and just we should know it, that's all. That is called magnetic shielding. Okay, now if I consider the force, how we have written for the magnetic moment and the force, okay, and the strength and the magnetic field, how we have written, that is nothing but F is equal to m into B I have written, isn't it? Now if I am going to write down, if I am going to express that magnetic field B, which is equal to F by m, okay, or simply B is equal to F by m, the force. Okay, so that we can write down. Now what is the SI unit of this magnetic field? So there are several ways to write down the magnetic field SI unit. The SI unit of force is Newton for the magnetic, that is the pole strength, not magnetic moment, that is the pole strength, ampere meter we are going to get, ampere meter we are going to get, or else we can write down in terms of joules, in terms of force. Okay, in terms of joules, if you write down, you are going to get ampere meter square, ampere meter square. Again you can write down in different manner, that is nothing but which is equal to volt second ampere meter square, volt second ampere, sorry, volt, that is volt, the current gone to the volt and becomes ampere, sorry, volt second and meter square. Then we have Weber per meter square, Weber per meter square, or else together everything we are going to call it as Tesla. Okay, these are the SI units. Okay, or any of the units, all are in SI units only, SI units only. Okay, everything is SI only, there is nothing but exiguous unit. Everything is SI units. Any of the equation you are going to get the question means for the magnetic field any of the unit they may give. Okay, most of the cases these are the units are used, these are the units used. So don't think that if they use also you have to change. No, there is nothing called you have to convert or to any of the quantities. You can directly substitute and you can get the answers for this. Okay, that is about the magnetic field. Now what we have studied about the magnetic field, we have studied some of the things like there are characteristics of the magnetic field lines and SI unit and all. Now when you are going to write down the SI unit, you have to write down the dimensional formula of this, dimensional formula for that. So what was the first dimension? That is force per ampere and meter. No, so the magnetic field I can write down dimension formula. I hope you know to write down the dimension formula, all those things, because every quantity we are going to write down in terms of m and l and t. Okay, for example, I am going to take volume is equal to length into breadth into height, means the dimension formula of volume is L means length, breadth means also it is length, height means also it is length, so it becomes L cube. That is the dimension formula of the volume. And acceleration means or velocity means all those things. I am not going to repeat once again here. So this is unit. No, this is unit means it is a force quantity. This is ampere and meter. Ampere means it is the basic quantity only. You have got to write down A itself. Okay, so it is ampere. Meter means that is length. No. Okay, then Newton means m/L/T minus 2. No, SI unit of, the dimension formula of force, that is nothing but force is equal to m into A. You are going to write down m/L/T minus 2. L/T minus 2 is for acceleration. In that way we are going to write down. So together what happens? You are going to write down L cancels, m0 A T minus 2. You are going to get m A inverse A inverse T minus 2 you are going to get. This is the dimension formula of the magnetic field. Okay, that is the thing. So there is a unit that is nothing but CGS unit. Okay, for magnetic field. Okay, there is a CGS unit for magnetic field. The CGS unit for the magnetic field we are going to call it as Gauss. Okay, so what is the relation between CGS unit and the SI unit? Tesla. Okay, so that is nothing but 1 Gauss. We are going to write on it as 10 to the power minus 4 Tesla. See, Tesla is the greater unit, Gauss is the lesser unit. No, so 1 Gauss means 10 to the power minus 4 Tesla. Okay, like that. Okay, so this is what about the magnetic field we are going to talk about. Now when you talk about magnetic field, there are two types of magnetic fields we can say. One is uniform magnetic field, another one is non-uniform magnetic field. So what do you mean by uniform magnetic field and non-uniform magnetic field? Most of the cases we are going to talk about uniform magnetic field. At any places the magnetic field remains constant or same. Okay, wherever it is go, wherever it is. Say for example, now north pole is here, means it may be here, it may be here, it may be here. We are going to talk about uniform magnetic field, means that points, any points the magnetic field remains same. Okay, then non-uniform magnetic field means, uniform magnetic field means the magnetic field is both same in magnitude and direction, but non-uniform means it may be different from the direction or it may be different from the magnitude. Okay, in that way. So we are not going to talk much about non-uniform magnetic field, only for the conceptual questions will come. For that magnetic when non-uniform magnetic field you have to when conceptual questions will come regarding that concept, you have to answer. That's all. Okay, this is what about magnetic. Okay, so now magnetic induction means what? Okay, so magnetic induction means the word magnetic field itself because of the any of the charges. So now north pole is there here. Okay, now what I will call it is magnetic field, or I will call it is magnetic induction. Okay, because of that north pole magnetic field generated, that is nothing but magnetic induction in that way. So magnetic induction they may call, or magnetic field they may call, the one and the same itself, okay, or similar, the magnetic field generated, okay, that is the thing. We will talk about magnetic flux. So you must have heard about electric flux, right? So what is that electric flux? Electric flux are nothing but electric field lines passing, okay, through the area, isn't it, per unit area. So similarly magnetic flux is nothing but, or magnetic field or magnetic flux is nothing but magnetic field lines passing, or magnetic lines of force. Magnetic field lines or magnetic lines of force, one and the same. So in different ways we can say it. So magnetic lines of force are nothing but the number of field lines, magnetic lines of force or magnetic field lines are passing, okay, normal to the given area, passing normal to the given area. So we will denote it as in this way, and this is a scalar quantity. It is a scalar quantity. Now I have given an area like this. I have magnet like this. So all magnetic field lines are passing normally, isn't it? Now what I have kept in this way. Now what I will do, I will kept in this way. Okay, north pole is there, magnetic field lines are, which are the magnetic field lines are passing normally? Okay, normal means this in this way, no, the component of this, no, the component of this, that is nothing but, okay, B cos theta. So pi, which is equal to B dot area vector, the passing normally means BA cos theta you are going to get, okay, BA cos theta you are going to get. Now in which direction it will be? It is always perpendicular to that. Now why area is taken as the perpendicular? Area is nothing but area vector n into a times, n is nothing but the cap n vector, that is perpendicular to that area. Any of the area you take, we are going to consider a vector which is perpendicular to that, that becomes a area vector. So the magnetic field lines passing along that, I can say, or else the magnetic field lines perpendicular to that area. How I can say perpendicular to that area? So all those magnetic field lines must pass through it, no, those are nothing but perpendicular to that area, okay, like that. So just you have to remember this BA cos theta, this much is sufficient for us. Now what is the formula, or what is the dimensions of that? See, magnetic field dimension, what did you write? That is nothing but dimension is mt square A inverse you write, isn't it? That is the magnetic field. Now area means m square, okay, length, sorry, area is nothing but length square, length into breadth, no, L square you are going to get. So m L square T minus 2 A inverse becomes the magnetic, the dimension formula of the flux, formula of the flux. Now what do you mean by magnetic flux density? So it tells about how many number of field lines are passing per unit area. It tells that how many field lines are passing per unit area. Magnetic flux density means more flux means more magnetic field, less flux means less magnetic field. So magnetic flux density is nothing but magnetic field lines, okay, or flux lines passing per unit area, okay, unit area of cross section. Okay, that is nothing but which tells about the magnetic flux density. So how many number of field lines are there through that area? See, area is there, now 10 lines are passing, okay, 10 lines, in that 10 lines are there perpendicular, okay. So per area 10 lines per area are there, that becomes magnetic flux density, magnetic flux density. Now same way you are going to give the expression, or magnetic flux density is nothing but same as that of the magnetic field we can write down, and the dimension formula will be same. Okay, so in that way magnetic flux density also we can call it is, and the SI units or CGS units already we have discussed, isn't it? So this is the thing, the magnetic flux density and magnetic flux. Okay, magnetic flux density is nothing but magnetic field, you can say magnetic, but flux is nothing but a scalar quantity. Magnetic flux density is nothing but magnetic field, I can say, or those number of lines passing through unit area. Okay, so now we have different notations, that is magnetic flux density or magnetic field if you consider, and intensity of magnetization, all those two you consider, means there are different notations are there. Okay, so we have written it as magnetic field, intensity of magnetization, or magnetic moment, magnetic intensity, like that, isn't it? So we have written B, we have written H in our regular classes, isn't it? So if you are having, see, if any of the material is there, you are going to apply some magnetic field that. Okay, how much it will take? Now for 10 seconds or 15 seconds I am going to apply the magnetic field for that, and I am going to leave it, I am going to remove it and somewhere. Now what is the magnetic field lines are present in that? Okay, that is nothing but the sum of, right, that is nothing but whatever it has taken. Okay, sum of nothing but magnetic moment generated plus total magnetic intensity, okay. So intensity of magnetization or magnetic intensity, okay, different. Intensity of magnetization means, or intensity of magnetization means how much it can magnetize. Okay, so in that way, so we have studied. So we are going to learn write down the relation of that. Okay, you can write down, that is magnetic flux density is equal to mu naught into H, that is for vacuum, and mu into H, which is equal to for the medium. Mu naught is nothing but permeability of the free space, and mu is nothing but the permeability of the medium, and H is nothing but we have written magnetizing force or magnetic intensity. Magnetic intensity means nothing but you are going to apply magnetic field to a material. So inside magnetic moment is generated, no, that is nothing but intensity of magnetization. Okay, intensity of magnetization, and magnetizing intensity is developed, or so two terms are there, intensity, it may confuse you, that magnetizing force you take. Okay, one is magnetizing force and magnetization is developed. Okay, so we have already discussed in our regular classes, that is nothing but when solenoid is there, you are going to recoil with the wire and you are going to pass the current, means some magnetic moment because of the magnetic field, one magnetic moment, magnetic capacity is generated. No, that is nothing but it behaves as if like a magnet because of its current, that is this, the magnetizing force. Okay, because of the current, plus because of that current inside all the domains are or the atoms are arranging in such a way that, and it develop its own magnetic magnetization, and that magnetization is m by v, or magnetic moment per unit volume, that we have studied. Okay, so total magnetic field becomes H plus I, no. So generally we can write down in this way also, because it is directly proportional. More and more magnetic field you are going to apply means, okay, that we have studied by applying the current. Here the same formula you are going to apply by applying a field. Okay, so what we have done, one solenoid was there, you are going to apply the current. Because of the current, one magnetic field is generated, that is magnetizing force is generated. Because of that magnetizing force, again inside it turned into magnet, converts into magnet. But now we are not going to connect any of the current here. So what we are doing, one metal piece is there, means powerful magnet we are going to bring, no, powerful magnet we are going to bring. Okay, in this way, so magnetic field is applied. Okay, so again magnetizing force and magnetic moment or intensity developed inside that we can write down. So one more thing, that is nothing but magnetic flux is nothing but is the number of lines passing per unit area, right, with perpendicular to the area. Okay, the SI unit of the magnetic flux is nothing but Weber only. Okay, Weber. Okay, and magnetic field becomes Weber per meter, no, because Weber per meter square pi magnetic flux line per unit area, no, that is B is equal to A, that we have studied. So CGS unit of flux density is nothing but Maxwell. Okay, the CGS unit of flux, okay, magnetic flux is Maxwell, and the SI relation between 1 Weber, which is equal to 1 into 10 to the power 8 Maxwell. The relation between Maxwell and Weber is 1 Weber is equal to 10 to the power 8 Maxwell. Okay, this is what about magnetic field lines we can talk. Okay, so this is about magnetic field lines. Now some of the arrangement I have written here. Okay, so this arrangement is nothing but two magnets at the center. They have perpendicularly we have arranged, or perpendicular they are attached. Okay, half of the magnet is in this way, half of the magnet in this way, and south pole comes here, north pole comes there. So magnetic moment will be, we can write down in this way. Now what happens, this is nothing but Earth's magnetic field. Somewhere in the direction Earth magnetic field is there, which makes an angle theta. Okay, now so they may ask you to give in such notation or such arrangement they can give, and they may ask you to find out the magnetic moment, all those things. Okay, now what are the relations we know? We know that, see, in equilibrium, see, this will apply to some external magnetic field is there, this will provide torque to this also, provides torque to this also. Okay, at equilibrium what happens? At equilibrium torque because of 1 which is becomes torque because of 2, right, and it will be stays somewhere, no. Then we can write down torque because of 1 is nothing but what? mb sin theta, no, because of 1 I am going to write down in this way. Okay, so m1 I am going to write down, b is same. For torque 2 which is equal to mb sin theta, but what is that theta? Theta is nothing but 90 minus theta, no, because both are arranged in the perpendicular direction. So 90 minus theta become sin 90 minus theta, that you can write down cos theta, all those things, but it is mb, m2 and b. So here you can, by using these relations, you can find out the magnetic moments or the magnetic field strength. Okay, you can find out. Okay, because these are similar, no. Okay, need not to give that torque value. Okay, so that time you can find out, since angle is given you can find out that. Okay, this is no need to by heart that, but arrangement how and all we should know. All the cases when you are going to write down the applying for the equilibrium case, we are going to apply for the equilibrium case. Next what happens is, one magnet is, see, one magnet is there, that is N2, it is north of this magnet, second magnet, south of the second magnet, north of the first magnet, south of the first magnet, which makes an angle theta 1 and theta 2. Now how to find out the relation, how to find out the net torque. So here net torque means, see, this arrangement is different, that arrangement is different. Okay, so net torque is nothing but both are rotated, no. So net torque I can say net torque which is equal to tau 1 plus tau 2. Okay, so you have to find out the net torque means, you can write down in that way, that is which is equal to mb sin theta 1 plus mb sin theta 2, that is nothing but m1 b, you can take it out. So what is this actually? m1 sin theta 1 plus m2 sin theta 2. This we have written for total torque, this we have written for equilibrium, that is also for equilibrium only. Both torque are becomes equal, I can say, and I can write down to find out the momentum and all, find out the magnetic moment also. So to find out the net torque also we can write down in this way, because vectorial sum, right, the magnet that torque. So next one what actually says is there are two magnetic fields are there. Okay, there are two magnetic fields are there. Now one magnetic field needle you are going to kept, which is having some magnetic moment. Now what happens is two magnetic fields are making an angle 75 degree. Two magnetic fields are making an angle 75 degree. When you are going to keep the magnetic needle, it makes an angle of 30 degree. Then what is the ratio of B1 by B2? What is the ratio of B1 by B2? How can I calculate? Similar to this I can calculate. Similar to it was making. So here also same, no, one magnetic field is here, one magnetic field is here, one more magnetic field, but we have taken magnetic moment. But that is reverse the case. At the case of magnetic moment they have given magnetic field, at the case of magnetic field we have given magnetic moment. Okay, same way we can find out the torque, and we can at the equilibrium torque are equal, that is tau 1 is equal to tau 2. We can write down and we can find out B1 by B2. Can you calculate B1 by B2 how it is? Okay, can you calculate? Let's see, tau 1 which is equal to what? For the B1 we are going to write down, magnetic moment is same now, B is changed, B1 sin theta, tau 2 which is equal to m B2 sin theta. What is the angle here? B1? B1 makes an angle of 30 degree. What is the angle made by B2? The angle made by the B2 with the magnetic field is 75 minus 30. Okay, that is 75 minus 30, that is m B2 sin 75 minus 30. So T1 is equal to T2, we know that. M B1 is equal m B1 sin 30 is nothing but half, which is equal to m B2 sin 45, yeah, that is 1 by root 2. Okay, B1 by B2, B1 divided by B2 is equal to m cancels, and 2 by root 2, which is equal to, you can write down root 2 into root 2 divided by root 2, you can write down root 2 divided by 1 in this way. This is one of the problem, that's all. So if this cases will come, you are going to apply for what are the cases you are going to apply? That equilibrium cases you are going to apply, and the torque cases you are going to apply, so that you can find out the magnetic moment and magnetic field you can find out, and angle also you can find out, anything you can find out. Okay, so this is the case with the external magnetic field. Let's see this kind of arrangement. Here already we are going to talk about, we will say that is actually generally it is external magnetic field. Sometimes they may ask it is Earth's magnetic field, whatever it is, some external magnetic field. Now magnetic field line is magnetic needle is there, but whose length is 2L, exactly at the center it is pivoted or it is fixed somewhere, and magnetic field is there, magnetic field somewhere is there. Now that makes an angle theta with that. That makes an angle theta with that. Now suppose you are going to apply some force by means of a string. What is the tension, or what are the things going to happen? Okay, so that we are going to talk about, but in the equilibrium case it just remains somewhere. Okay, now what happens, you are going to rotate it once again, or some string is there, you are going to apply some force. Then what is the tension? With the tension is nothing but the torque because of tension, isn't it? tension in the string, which is equal to because of the torque itself, isn't it? Some torque is there in the opposite direction or somewhere. I am going to apply force, means the same way it is going to come in the equilibrium. The force applied torque because of the pull, and torque because of the magnetic field remains same. No, magnetic field remains same. Now I can write down torque because of the magnetic field is mb sin theta. So what is sin theta always? Sin theta is nothing but magnetic field and magnetic moment. That is torque because of the magnetic field. But now what I will do is I am going to rotate it. I have tied a string and I am going to rotate it. Then what is the torque? It is not that torque. Earlier we have written mb sin theta, mb cos theta. Now I am going to apply some external torque and I am going to bring it somewhere. Then external torque is because of the tension of the wire, like that. How I can write down? See, in the system of particles you have studied. Okay, so one wire is there or like this in your object. At a certain radius r you have to apply a perpendicular force, isn't it? Now I am going to apply the force along the length. Oh, okay, you consider this board itself. Okay, so you think that one screw is fixed here and it can rotate. Now it is stable. Like this I am going to apply the force, means, or along the length I am going to apply the force, means that it is going to rotate. No, I have to change the direction like this: 10, 20, 30, 40, 50, 60, 70, 80. No, it was 0 now. 1, 20, 10, 20, 30, 40, 50, 60, 90. 90 means maximum. No, means along the length there is no force. Now what is that direction of that force? So I am going to apply the force in this direction, means no torque. Okay, so I am going to apply the force by making an angle theta in this way. No, so what we are going to do? We are going to write down a perpendicular. So this is theta, means this is 90 minus theta. This is 90 minus theta, and if it is theta, means this is also theta. Okay, this is also theta. So what is the angle? What is the angle? Yeah, force makes with this length, that is nothing but, again I can say 90 minus theta. Okay, total if you take, means this is 90 minus theta. Okay, so you can get torque because of the tension, which is equal to force into FL sin theta, RF sin theta, isn't it? RF sin theta you have written. So here also sin 90 minus theta you can write down, because of that it is nothing but cos theta, F into L into cos theta you can write down. That sign is doesn't matter, that's what it is, negative, positive, like that we can take here. Okay, so we are going to get FL cos theta, which is equal to in this way, or also I can write down FL cos theta, which is equilibrium. No, FL cos theta, which is equal to m b sin theta. M is nothing but 2L into small letter m b sin theta. This is FL cos theta. So what is this torque? This is the formula came because of the system of particles, from the chapter system of particles. Now what actually it is, one needle I have kept in the magnetic field and it will align in this way. Now what I am going to do? I am going to apply the force in this way, perpendicular to that. Not sorry, perpendicular to that. For this some angle, I don't know what is that angle, but that magnetic needle makes an angle theta with the magnetic needle. Now it is in equilibrium. What I am going to do? I am going to apply some force in this way, F. Okay. Then what happens? Because of the magnet, okay, I will bring it and I will stop it somewhere. Okay. Then what happens at the equilibrium? Because of mb sin theta, that is magnetic field, that torque is similar to that of the force because of the applied by me. This, that is nothing but YFL cos theta. because it is sine 90 minus theta, no? That torque is nothing but RF sin theta we have to write down, isn't it? You know, RF sin theta, system of particles. R is nothing but L here, and F is nothing but F is sine is nothing but sine 90 minus theta, sine 90 minus theta, isn't it? Sine 90 minus theta, and sine 90 minus theta will be cos theta, sine 90 minus theta will be cos theta, that we have written, and we can write down L, we are going to cancel it, and in that way we can find out the force, we can find out that theta, all those things we can do. So this is a general case, or this is one case of a problem. Now I am not pivoted this, or it is not fixed at the center. Okay, one length is more, little length is less, another end length is less, then that becomes R. So similar equation comes, right? Similar equation comes at the place of L, it becomes R. At the place of L, it becomes R, and you can find out the formula. You can write down the formula. That is the thing. So again, this I can minimize it. So F is equal to L cancels. 2m sin theta by cos theta is tan theta. Okay, in that way you can write down. So okay, we can write down 2lm into b. Okay, 2lm into b. We have written b sin theta. Okay, what we are going to get? Sin theta by cos theta, which is equal to tan theta, then L cancels, 2l m into b, isn't it? M means, so b is there, 2m b is there, which is equal to f is there, so b will be equal to f by tan theta into 2m. You can write down f by tan theta into 2m, you can write down. In that way we can do the arrangements, or you can find out the magnitude of magnetic field, all those things. So in this single expression, so here also if you write down means this becomes theta. Okay, this becomes 90 minus theta. You are going to apply. It may be always, see, it may be a force like this, it may be force perpendicular to that. Perpendicular to that means sine 90 itself, sine 90, okay, sine 90 is 1, so f into r it becomes. Okay, sine, earlier it was sine 90 minus theta here, but you are going to apply in this way also, this way also, this way also, no, perpendicular also, no, different ways they may give there. Okay, like that. Okay, while problem you are going to get means exactly we can write down the formula for that. Okay, and we have studied, just go through the problems and nothing else. When we do the problems, exactly at that time we are going to get to know about that. These are some cases of the problems itself. Okay, we will get the clear picture of idea of that. Okay, just go through the problems, that is sufficient, and keep any of the standard material. It may be any convenient for you, Singlish publication or MTG or errorless or any of the things, you can keep it with you, and if you want extra information you can refer other textbook, but one material you keep it along with you, that is as a standard material, that is sufficient. Okay, so as of now today we have discussed this much sufficient. Just go to the formulas. Okay, thank you very much.
Don't forget to like our video and subscribe our YouTube channel for all the updates.